Hey, good evening, everyone. I wanted to record a video about creating radical equations. So if I gave you two solutions, maybe one being true, one being extraneous, maybe I said, here are two solutions, but they are both extraneous. Create a radical equation that creates these two extraneous solutions. I'd like you to be able to do that. I signed that for homework last Thursday, and being that I didn't get any questions about it over the weekend, and I think the hints in the homework, maybe you all feel pretty decent about being able to do that, and that's great because it didn't seem to come up today also in class. But I know there's a trick, so it doesn't necessarily always quite work out that you got the exact true and extraneous solution you wanted. So I want that to be what you pay attention to in this video, and I will help you see the adjustments you need to make. Your process still is good, but we just need to make some small adjustments. So without any further ado, I'm going to try to use the Jamboard, which I'll also link as a resource, and record that. And I haven't done this in a little while, so please forgive me for being a little slow and cumbersome while I'm trying to get things connected and set up. All right, here we go. Gosh, I don't know if you see me anymore or not. I don't see myself, so I hope I don't do something crazy while we're working. Okay, so this is the Jamboard I'll link, and I'm going to write on it and talk as we go for the next 10, 15 minutes or so, or as I go. I'm going to consider the situation, create a radical, what I keep calling a radical equation. I don't know that that's a really formal term. I've picked it up from other places as well, so it seems okay. With true solution, x equals -3, and extraneous solution, x equals 2. And so number one, I hope you guys are, I'm just going to restate kind of goals. Number one, I hope you are able to confirm, okay, that I have a method that's just like, or very similar to what Lawler said. I knew how to do this. And number two, that you're certain that the radical equation you created does actually have this true and this extraneous solution. That's something I suspect some of you may have overlooked. And just as a reminder, when I say radical equation, I'm meaning something like this: a linear term under a square root equals some linear term. So this is the format I'm thinking when I say radical equation, okay? So first step is, well, I know that if I write this expression or this equation, the solutions will be -3 and +2. So now my strategy is just to perform some algebra that will cause 2 to become an extraneous solution, okay? So just by way of a little exploring, my first step is just let me multiply that out. Now I know that when I have a radical equation like this, typically to solve, the first step is squaring both sides. So I have a linear now equals a squared term, right? So I'm thinking, oops, darn it. Sorry about erasing that. I'm thinking this, I don't know what buttons I'm pushing anymore with this. It's been a while since I've used it. I'm thinking this term, which will be squared in the step before it, is really what would be right here, right? Because that's what I would get when I square it. But to square it, that means the result of having squared it has got to be a perfect square. So for example, if here I have x plus 1 equals something, and then I square it. So in other words, if I want this to end up being x plus 1, the step before that would be to square it. So x plus 1 squared is x squared plus 2x plus 1. right? Now, and that is not what I have here. I don't have x squared plus x minus 6. So this is not what we call a perfect square. This is what we call a perfect square. And I'm going to name that real quick. So I've kind of worked backwards because I should be going this way, but I wanted to point toward this is the end I'm looking for. How do I get there? Well, from here to here, or really from here to here is the big question, but it's not that hard. All I have to do is say, yeah, I'll use red. To get from x to 2x, I added x. So I'm going to note that I add x. Actually, I don't want to put it there. Let me put it over here. I'm adding x. And then from -6 to 1, I'm adding 7, right? So if I add x and 7 on that side, I have to add x and 7 on both sides. So this is the big step. From here to here, I just added x plus 7 to both sides. So in other words, that keeps these two equations equivalent, i.e. they still have the same solutions, but they're just written slightly differently. How did I decide to add x plus 7? Well, I jumped and I aimed for a particular perfect square. I figured out what that perfect square is multiplied out and then just figured out what the difference was to get there. Okay, so I have x plus 1 squared equals x plus 7. This is equivalent to each step before. So this has the same solutions as this. In other words, say again, this has solutions -3 and +2. Now, if I square root both sides, I have my radical equation, but I've possibly introduced an extraneous solution. So let's check. If I use -3, I have -3 plus 1 equals square root of -3 plus 7. That is -2 equals 2. Uh-oh. Uh-oh. That looks like that is not a true solution, but I wanted it to be a true solution. Let me check x equals 2 also, just out of curiosity. That says 2 plus 1 equals the square root of 2 plus 7. That says 3 equals 3. Uh-oh, again, that means it's a true solution, but I wanted it to be an extraneous solution. Let me go to Desmos. I'm gonna try to figure out, there we go, stopping share. F of x equals x plus 1. G of x equals square root of x plus 7. Let's go ahead and graph the auxiliary line. And it looks like I'm getting this at approximately -3 as the extraneous solution, where I wanted it to be the true solution. And same over here, x equals 2 is the true solution, where I wanted it to be the extraneous solution. Okay, so my algebra did not quite yield what I wanted. Wait, what if I made the linear term -x plus 1? If in other words, if I just swap the auxiliary and the true lines, now I have what I wanted, don't I? True solution at -3, extraneous solution at +2. So I just identified our first strategy for how do I correct. So I went through the algebra, number 1. Number 2, I'm checking to see if I'm right. And my check showed that I have it backwards. So let me try to make some brief notes here. I hope you're taking your own. Uh-oh. by checking solutions are swapped. Method 1 or strategy 1, what I ended up doing here was swapping the equation of the auxiliary line. I should write all that out. And remember, the equation of the auxiliary line is just the opposite of the equation of the line. I'm going to call it the true line. And so what I mean in this case, so here's where I swapped it, right? By just taking the opposite out in front. I could rewrite this if you prefer negative x minus 1 equals root x plus 7. So this here, in fact, does it. We have solved it and made sure our true solution is correct and our extraneous solution is correct. Next. Why did I pick x plus 1 squared here? Kind of glossed over that beginning, but what I was saying is we need to aim for a perfect square. Well, why did I pick x plus 1 as my perfect square? Could I use other perfect squares? So in fact, yes. So remember, we had x minus 2 times x plus 3 equals 0, which is x squared plus x minus 6 equals 0. And I needed to get it to a perfect square. You know what? That is a perfect square. And to get this left side from x squared plus x minus 6 to just x squared, I just have to move these two pieces over to that side. So look, all I have to do is say negative x plus 6. And now I have x equals square root negative x plus 6. Radical equation with those two solutions, right? Remember, we got to check. So quick check, let's put in negative 2 is negative 2, no, positive 2, right? Positive 2, is that equal to negative 2 plus 6? Yes. Dang it, we wanted 2 to be the extraneous solution. Let's see what happens with the negative 3 real quick. The opposite of negative 3 plus 6. So is negative 3 equal to the square root of 9? No, so wait, this is, so that turned out true. This turned out extraneous, but we wanted the opposite, right? So it looks like, once again, we can apply that previous strategy, and it should be that negative x equals the square root of negative x plus 6 gives us our solution. Because it takes me a bit of time to either write the check steps or go over to Desmos to check, I'll leave it to you to maybe even pause the video right now and confirm for yourself, but that should be good. Okay, now you should be asking, well, that was 2 examples, Dr. Lawler. Can I use really any, and do I always get this case? No, it starts actually getting a little trickier. I'm going to actually move us, I'm going to move back to Desmos one more time. I'm going to change. Okay, so I played with sliders earlier today in class. So you noticed the last worked example, I had x plus 0, or in other words, just x. And the one before that, I think, was just x plus 1, or x, yeah, I think it was x plus 1. So this is an example where it's x plus 1. Here is, look at my a term, x plus 0, x plus negative 3, x plus. So if I keep making a smaller and smaller and smaller, it looks like I keep getting 1 true and one extraneous solution. I'm not adjusting the square root graph because I want to illustrate I could pick an x plus something that might not end up with any solutions. So really, I just wanted to quickly jump over to the graph and show you I can't just pick x plus anything and then square it to be my perfect square. I might get actually 0 solutions. I'm going to make a little challenge here for anyone who wants the extension, the extra investigation. There is a way to define the parameters of what the a value could possibly be for your perfect square based on the square root. There's like a little formula we could create that says a has to be between this and this. If you're interested in developing that, that would be pretty amazing. But for now, I just want you all to say, I could guess something, and if it really is wonky, how might I adjust it? So let's take a look at maybe, I think, one more example where I pick something that's gets outside the realm of normalcy. Uh-oh. Okay, so my third example is, again, is basically, can I use any perfect square to make this work? Let's hope my next example gives us a good sort of bad example, I guess. So we're there. What if I picked x plus 5 as my perfect square? So x plus 5 as my perfect square looks like this. If you need to double check the arithmetic or the algebra, pause and do so. I always ask myself, how many x's did I have to add and how many constants did I have to add? So that tells me this side of the equation has to add 9x and 31 to be balanced. So x plus 5 squared equals 9x plus 31. X plus 5 equals the square root of 9x plus 31. Let's go ahead and just check these by hand. So let's see. -3 is supposed to be the true solution. So let's check that. -3 plus 5. I'll put true there to remind me, equals -27 plus 31. So 2 equals 2. Looks good. X equals 2. It's supposed to be the extraneous solution. 2 plus 5 is supposed to equal 18 plus 31. That says 7 equals 7. Ugh. That's not extraneous. That worked, right? So I think I will end here by saying not all cases. So you might guess right away, and what we have here works just like we expected it. Or they might be flipped, like in this case. In this case, they were flipped. So what we realized we could do was just take the opposite of the linear term, right? Here was another example where we saw that exact same problem turn out. So we just flipped the linear term again, right? But here, this time when I randomly picked my perfect square, I got both solutions being true. So now if I flip and make this a -x plus 5, you might guess it's going to make both solutions extraneous, right? So what's happened is I haven't picked a useful term here. Like I said a moment ago in this challenge, you might do a little analysis and you can find out like a boundary by which that linear term has to be based on this radical equation. Like it has to be within something and something to get something we want. But that's advanced, that's extra. For now, my point is you can get in there and more or less, guess and check. Desmos can always be a place to help you check things out. But just know that it's not just straightforward. You're going to have to get back at the end of the day to check that the solutions you created are true in the way you wanted and extraneous in the way you wanted. And it might not match up. You might have to adjust. I hope that was helpful. I'm sure you all have gone through this and maybe paused and checked some math a few times. You might even give yourself one last challenge to say, okay, what if I did first pick x plus 5 squared? What should I pick next? You might try x plus 7 squared and see if that makes it even worse, which it will, I believe. And you might move back toward the ones we were using before, x plus 1 and x plus 0, and just confirm, like, if I get this bad one, what can I do? I'm also welcome to email. So if you want me to clarify anything in this video, email me. And it can also be a question the first 15 or so minutes of class on Thursday. All right, I hope that was helpful, some deeper insight into creating these radical equations. Have a good evening, everyone.